Hello there. Welcome to another problem session. So there are a whole bunch of problems we want to do in static electricity. So this is where the electric field of formula for electric field is known, and we want to find formula for electric potential. Okay, so this is a very common situation. For instance, if I give you this is my source charge, right? If I give you a point charge as a source charge, so source charge sits right here at the origin of a coordinate system, and so if anywhere in this region at distance r, this is the spherical coordinate r, the radial distance r, then electric field has this formula, and this is a unit vector, and this is the magnitude or strength. This is the strength of the electric field, and this is the direction of the electric field. So there's only one charge here. This is, we are calling this source charge. There is no test charge or anything, so we're not looking at force or anything on the charge or energy of the charge. We're just looking at electric field that this charge is producing. This is given. So in our problem, this is given, and we're supposed to find electric potential at point P. So the fundamental formula is this. We talked about formula like this in another video. That's a electric field and electric potential relationships, and this is a fundamental relationship, and it's only true for a static electric field. So if I had if I didn't have a static electric field, then electric field actually, say if electric field depended on time, then this will not be minus del V of RT. Okay, so this would not be correct. Actually, it will usually be written as del V plus 1 over C dA dt, which is, this is related to magnetic field. Okay, and that's for another time. Don't want to complicate it. So we're not having dynamic field, we're just having static field. Okay, with that caveat, we just have to do this integral, right? So to find, we're not going to get a V at P, we're going to get a VP with in relation to some other point. You can see this is V of P, then this is some another point. So let's see if I pick a point P, point A, which is kind of in the same direction as that. So if I go from A to P, that's the path. I'm going along this direction. I could pick any other point, and I can get there by 90 degrees to that direction. But let's pick for convenience a point along this radial path, okay? And to do this integral. So with respect to this, let's see, this A is RA, and so this distance RP is R, okay? So we're going to use RP, let's call it RP. And so let's set this integral up. So this integral requires your DL. So DL will be a little path, so from at distance R, and this path is dr, and in the same direction as that you had R. So DL is dr, you had R, and these are in the same direction, so E dot DL will simply become KQ over R square dr. And then if I integrate between A to B, RA to RP, RP is the point at we want the potential, so that's the integral I want. So I'll get a VP minus VA equal to this, and you have a KQ over R square dr. So when I integrate, this becomes this minus kills this minus, okay? So this is going to be KQ over R, RA, RP, and so doing it out, KQRP minus KQ over RA. Now you can see that so this is, I take A was a reference point, so it seems like a difference is cancelled out. Whatever, there's some difference between them, can't cancel out. So if I were to take this as a reference and say it was a reference, A was reference, and so this will correspond to the reference part. So if I want to get the reference part go to 0, I have to pick A at infinity. So this will go to 0 if A at infinity. So this will go to 0. So with this choice, so reference at infinity, V at any point P is going to be, V at any point P will be KQ over R at P. And that's the distance from the charge to that point P, and charge being at the origin, we have a straight out distance. So this is a formula with this reference is common to memorize. There are many applications of it, right? If I have 2 charges or 3 charges, we just add up the potentials. So let's just look at one application of this formula, okay? A simple application, this formula can have 2 charges. I have a charge here and a charge here. So say I have a plus Q1 and this is minus Q2, and I want this is the point P, I want the potential at P. So it will create a potential here. So let this distance be R1 and let this distance be R2. So these are direct distances, not from the origin, but from this point to that point. So here V at P will just be 1 for each thing. So K Q1 over R1, and this is negative, then it's going to carry the negative with it, Q2 over R2, and that will be the answer. So if I had any number of charges, I could just do it out. Many times people put a triangle, I put charge here, charge here, charge here, and say what's the electric potential at the centroid of the triangle, and then you just have to add up from each of the charges. You can have 3 charges like this, and what's the electric potential over here. So it's very easy, there's no vector to work out, they're just adding up this thing, right? Okay, so that's point charges and lots of applications of that formula. All right, so you need to kind of memorize, and you can see the reference has to be memorized with the formula, because without the reference this is no good. Okay, next up in terms of this kinds of formula generation is of a the source charge is a infinitely long wire. So this is actually Coulomb over meter, with the charge density being constant. This is a fictitious problem. You can there's no infinite wire and things like that, but this is because if you have infinite wire, you can have a cylindrical symmetry, and you use Gauss's law to produce this formula. So this formula produced by using Gauss's law. So there's a video you want to see how this formula will produce. But suppose I have been given this formula for electric field, and I want to know what's the potential is going to be. Okay, so we do exactly same thing. Once again, we do use this formula. So we need to think of a DL on a path. So I'm gonna again say, let's say A is here. I can't put the origin here because then electric field there will s equal to 0 will be infinite. So I want to avoid the origin, so I will just put it over here, say A, so that I'm in the same direction as the electric field on this path. So that's the path. And on that path, I pick a little dl, right? So it's along that path. It's at s. Let's call that distance s. And so this one is dl. And the dl is going to be distance ds. This is cylindrical coordinate radial distance. And it's going to have a direction same as unit vectors us. You had s along this direction, so unit vector is along the same direction as this direction. So this is going to be a dl. So we just plugging in here, E dot dl will simply be k lambda over 2 pi s ds. So now if I have a Vp minus Va, A is going to become a reference for us, is equal to, and that will tell us where to place the reference. You will see I won't be able to place the reference at infinity in this case, okay? In the point charge case, reference was at infinity, but here it won't be. But let's work this out. K lambda over 2 pi epsilon naught. Epsilon naught is missing. 2 pi. There's no k here. There's no k here. There's no k here. Okay, so it's a 2 pi epsilon naught. There's no k here. 1 over s ds, and it's negative, and integrate from a to p. So what do we get here? We are going to get minus lambda over 2 pi epsilon naught log. So if this distance s of p and this distance s of a, so log, so s of p, let's call this distance from here to s of p, this distance from here to s of a, so log s of p minus lambda minus plus lambda 2 pi epsilon naught log s of a, or s of p over s of a. You can combine these two logs, right? Now the choice of, now we can say choosing reference. So this is going to be reference. So where should we place reference so that this goes to 0? So the reference, this will go to 0, will go to 0 if SA is in the same unit as this, is 1 in unit of SP. How do I need this unit SP? Let's write this equal to minus lambda over 2 pi epsilon naught log SP over SA. And this, because this is log, this is dimensionless. So unit of SA has to be same as unit of SP. So in the unit of the same distance unit that we're using for this, this will disappear, and then we can set reference to 0. Then V at P is minus lambda over 2 pi epsilon naught log S at P. And reference V equal to 0 at S equal to 1. So this formula goes with that, so this will be the formula for that. It's very easy. You got to do the integral, but let's go back and look at what happened. First thing was we needed to find a path to do dl. So I picked A suitably so that I can do a path, and then on that path I need to make sure what the formula will be, and it tells you I've got to integrate over ds. So these will be the limits in S, so the SA and SP, because I'm integrating over S. and then I have to suitably pick a reference so that I can get rid of this. I can set the potential at 0 at the reference. So this said this reference should be at 1. If this unit is in the meter, then it will be 1 meter. It's not at infinity, because if you set this SA at infinity, then this will become blow up. This will become infinite, and so it can't be set at infinity. So, you know, reference is not always at infinity. And there is a reason in this case. You can see the charge is actually going all the way to infinity itself. So whenever the charges get distributed, whether on a plane or on a line, they go to infinity, then there is this mathematical problem that you face, that you can't really put the reference for electric potential at infinity also, okay? Because there will be some charge at infinity in some direction. Okay, so that's one of the caveats. That didn't happen for point charge, but it happens for this case and this case, okay, and long cylindrical shell and charge infinite torque. So these cases, this case, this case, this case, and this case, you cannot put the reference at infinity. Now these will be other cases where you have a spherical shell or a spherical solid. They are finite size objects. There the reference can be put at infinity, okay? So let me carry on and do planar sheet charge. Before we do that, let's look at the formula having some application. All right, each formula has a whole bunch of application. All right, so here is a famous application for this formula. It's two parallel wires, one with this charge density, another one is exactly same charge density but opposite sign, okay? And so what's the electric potential at a point between them? So this distance is S plus and this distance is S minus. And this actually you can just use here just formula for each one of them and use superposition principle. So the V plus V minus, right? So V plus is a minus, there's a minus here, minus lambda over, for positive lambda, 2 pi epsilon naught log S plus. Then we have a add minus lambda over 2 pi epsilon naught log S minus. This minus cancels out, and so cancels out, and then this will be as simply minus lambda over 2 pi epsilon naught log S plus over S minus. So when you can see at equal distance, those points, when this becomes 1, the electric potential is 0, right? Okay, so it's a okay, this is one application. You can think of other applications like that of this, as long any number of line charges and in any configuration, as long as the distance from those line charges to the point P you can compute, you are able to use this formula. Okay, let's try to do the number 3. Okay, this is a very important problem, appears a lot in applications. So here is a this is given as before. This is given. How is it found? Again, you can use Gauss's law. So found using Gauss's law. For instance, we have a we have, say, maybe this is charge sheet is all positively charged, and it's a sigma coulomb over meter square charge on it, and maybe your distance little d from the plane and is pointed in the normal direction. Okay, if this positive, then it's pointing like that. Okay, so what's the VP here? Well, I do exactly the same thing. So let's draw a little bigger picture for ourselves. So we're looking at this point, and this is the unit vector in a normal direction. So this is the point P, and we're gonna pick a DL. We're gonna pick a point A where I can do it. A will become a reference. So I'm gonna pick some point A over here, and we're gonna do the integral from A to in the same direction, and where this normal hits the plane. Okay, that's just this will become reference. Okay, will be used for reference, choice of reference, for choice of reference. Okay, again, it's quite easy to see. We can just call this z-axis, and then this will become, from here to here is z, and this thing is dz k hat, and this is equal to k hat. So dl is going to be simply dz k hat. This little tiny vector, displacement vector, will be like this, right? So E dot dl on this thing, the formula is sigma over 2 epsilon naught, and this is k hat dot k hat. This just becomes dz. Very easy. So v at P minus v at A is just turns out to be minus sigma over 2 epsilon naught dz. So if this is at ZA and this is ZP, so ZA to ZP, and this sigma over 2 epsilon naught ZP minus ZA. Okay, now I need to pick some reference, right? And one way to have the reference is 0 is excuse me, that if A was right on the plate. Okay, now you say you can't put right on the charge, but because this charge is distributed, okay, the density on a point, the charge will be can be considered to be 0 on a single point. So I can put A here. So if the reference is at z equal to 0, then this can be reference 0. So formula just turns out to be V at P equals to minus sigma over 2 epsilon naught 2 epsilon naught z at P, and reference is right on the plate, reference at z equal to 0, reference of v equal to 0 at z equal to 0, which is kind of completely agrees with this formula, right? So if you have a positive plate, this value becomes, as you go further away from the plate, you get more and more negative potential. Okay, now again, you couldn't put at z equals to infinity, you can't put reference out here at infinity, because at infinity this will become potential will become infinity. This term will become infinity, and so will not be, I want reference to go to 0, so this would not be corresponding. So I we usually pick a reference that is finite, where the potential will be finite, and typically that finite value is taken to be 0, and that's the case. Now this formula has a lot of applications. So a particular application I'll show you just now. So one application of this formula for a single plate is a two-plate system. One is negatively charged, another is positively charged, and there's a point P from the negative plate. It's a distance d minus, and the positive plate distance d plus. And we want to know what the potential will be here. Okay, so I went ahead and because this point P is on the left side, and while we worked out with the right side, the z-axis is going through the right side, right? So there was no sign problem here, but if it's on the left side, the z coordinate for this will be negative. But we want, you can see the E and dl in the same direction. So go from here to there, it's going to be exactly the same integral, and it's going to be negative because we have put reference 0 at the positive plate. Now we want to, when we do this plate, we have to pick one reference 0. So this will be reference 0 for us, not this one. So when we find out the potential at P, so potential at P should be coming from the positive plate plus from the negative plate. So from the negative plate, this one, using just this formula, is going to be minus sigma times d minus over 2 epsilon naught. So this is sigma d minus over 2 epsilon naught. So we need to figure out what v plus will be, how much from here to there. Well, reference is from here to there, so I need to do the integral from here to there, right, for the potential of this guy. I'm not going to do from plate to this, I want to do reference to that point. So this will also be sigma d minus 2 epsilon naught. And so this is going to be sigma d over epsilon naught, d minus epsilon naught, plus sigma d minus over 2 epsilon naught. And so you have a sigma d minus over epsilon naught. So that's the answer for potential at this point. Actually, you could do this not as an application of this formula, but you could do that as directly integrating it. And let's do that out. That's a really much easier calculation, and you don't have to do a superposition. So we want to say we want to do this. We want to do this in this integral in this situation. So we would need electric field from both these plates, electric field here, and it comes from negative place and positive place. So this actually would be given to you as sigma over epsilon naught from the negative plate up, actually towards the negative plate. From electric field will be from positive plate to negative plate. So this u hat will be positive plate to the negative plate. So that's the electric field. So we have this situation, and we want to take this as a reference. So from reference to the point P, the dl, we set up the dl. dl, it will be along the z-axis, dz along the z-axis, and electric field inside there at that point using this is sigma over epsilon naught from positive plate to negative place is minus k hat. So if I do this dot product, I get a sigma over epsilon naught dz, and with this minus, and I go from reference to the point P, the reference to P, this should be Vp. And so this is going to be sigma over epsilon naught d minus. So you can see right away, this is, if you do first superpose the electric field and then you do the integral, that also works out the same way. Okay. Now on to these other things, other cases. I would say you set up the, either look up the formula or use the Gauss's law to find the formula for the electric field and try to do these integrals. So these guys are very instructive and very important examples. Maybe in the future I will do some videos on each one of them. Already this video is very long, but I just wanted to make sure that you understand that just one formula can give you can solve a lot of problems for you if you know the electric field, how to get the electric potential. That's one thing I want to do. And second thing I wanted to do was to show you the nuances of how you set up the references. The references comes with choosing where to place point A so that VA will be 0. And that has to do with how do we choose DL. So there's like a whole bunch of little tiny steps that are very maybe confusing and challenging at times. But then once you do a lot of these problems, you're going to be very good at it. And you will appreciate that electric potential requires a suitable reference for you so that the formulas come out simple. Later on, we're going to use this electric potential to study the motion of other particles, other test particles in the static electric field. I can't overemphasize this. There's a whole thing that we're doing is all about static fields. Okay, the dynamic fields, when we get to it in a few weeks, they're very interesting and much more challenging, but they're also much more interesting. Okay, I'm going to stop here and hope to see you in another video. Okay, bye.